It's been telling me over and over again that my mic has been muted this whole time. Sorry about that. All right, so starting over. Hey, y'all, it's Mr. McKinney. It's nice to see you. So this is going to be your lecture for Chapter 2, The Chemistry of Life. With this chapter, we're kind of building up from Chapter 1, how we talked about the organization of life, how we start with atoms, go to molecules, and then those build up to cells and organisms and the whole biosphere eventually. So this chapter is just starting with atoms and molecules. We're going to get into what makes up an atom, the different subatomic particles, types of bonds, properties of water, acids and bases, and then macromolecules, your 4 macros. If I have time today, I'll go through all of that, but I'll probably be able to get through kind of the first 2.1 to 2.4. That covers that first soft chalk that you have. And then section 2.5, that's the macromolecules, that's the second soft chalk. So do kind of make note, if you saw on Blackboard, that this chapter covers 2 weeks. We get into week 2, and then it's going to bleed into week 3 as well, and then you'll start chapter 3 next week as well. So it kind of moves all in there together. So just make sure you're looking at those due dates and following along with that. All right, so I'm going to go ahead and get jumping into this chapter. I'm going to go through some of these slides maybe a little bit faster if the material just is not as in-depth. So we're getting into this idea that we are starting to create life. We're starting to build things together. And so if you think that everything is made up of matter, everything around you, everything that you see has matter, has mass. Even the air around us, even though we can't always, detect it, and it's kind of invisible, we know it's there. Wind can blow against your face. When you don't have it, you notice it. When there is maybe too much and you have air pressure pushing down on you in the storms, right? We notice air in that sense. So all of these things have matter, even if we can't see it. And so we're going to start talking about what is it that makes up those things and how do they join together? How do they form these kind of complex shapes and organisms that we have? Matter is made up of elements. Elements are atoms. An element is a substance that has certain properties. And so the most common elements that we have in life are carbon, hydrogen, oxygen, and nitrogen, as well as phosphorus and sulfur. So carbon, hydrogen, oxygen, nitrogen, those you're probably pretty familiar with in terms of those elements, but phosphorus and sulfur, I'm going to give you a second just to kind of think about where do we have phosphorus and sulfur in our bodies? Where might we have that? If you said DNA, proteins, things like that, you are absolutely correct. That is where we see most of those phosphorus and sulfur molecules are on those things, and they're nucleotides, and so amino acids, and so they're very abundant in life. You're probably familiar with the periodic table of elements. I'm not going to break it down too much. I'm not going to really test you heavy on the periodic table. You should be familiar with a lot of those 6 atoms that I just mentioned. You should be familiar with those, their numbers, the symbols for them. So here you can kind of see, here we have a carbon atom. You have the carbon symbol in the middle with its atomic number, its atomic weight. I'm not going to ask you about numbers and weights or anything like that. For me, it's really just going to be getting you to understand and just recognize these elements, their names and their symbols. So again, just to kind of hint on that, an element is a thing that has properties to it. And then an atom is the smallest form of that element. So an atom of hydrogen has those characteristics of hydrogen. But an atom is also made up of something. Up until like the 1950s, they thought that an atom was the smallest unit of life, the smallest organized, not unit of life, but the smallest organized matter in our universe. And then we sliced open the atom and we came up with different subatomic particles, right? Subatomic, below the atomic level. Electrons, protons, neutrons, those kind of things. Those are what really give each atom its own characteristics, all of its unique characteristics. If we think about the shape of an atom, how it has, the central nucleus with inside the nucleus, that's where you're going to have a lot of those protons, neutrons, electrons, those kind of things. That is really what's going to dictate how that thing behaves. So I am just real quick wanted to pull up an image for us so I can work with that. There we go. So here are these images of atoms, right? So you're probably familiar with something like this shape. Right here in the middle, that's the nucleus. So the center of the center of something is going to be that nucleus. So in here, this is where we have the protons and the neutrons, the positive protons, neutral neutrons, and then out around it are the electrons, right? The negatively charged electrons in this kind of cloud orbiting around uh, the uh, the central nucleus. So with that, let me bring back up the notes. Great. Uh, so again, the combination of protons and neutrons in the nucleus, and then electrons in the cloud, those combinations give an atom its characteristics of that element. Okay, that can start to shift. So isotopes are different forms of the same element. So you can have an element of carbon, but you can have different forms of it. Carbon 12, carbon 13, carbon 14. Each of these are different isotopes, meaning different variations of the same element. So they're all going to have similar properties of that carbon, the elemental carbon, but they're each going to behave a little bit differently. And the thing with isotopes is that they are unstable. So you can see that in here we have 99% of carbon atoms are this carbon 12. That's what you're used to. C12, carbon 12, that's normal carbon. That's what's in you. That's what's in me. We got carbon 12, right? 6 protons, 6 neutrons, equal weight, right? That's where you get that, the fact that carbon, the 12 comes from its weight. Its weight is 12 AMU. The rest of carbon, 1% of it, is actually unstable radioactive isotopes. And so that's similar when we talk about an isotope. It's a radioactive isotope because it's going to be giving off energy because it's not as stable as it could be. And life always goes to stability. That's what we get into when we get into bonds, is that bonds are all about making things more stable. And so with carbon 13 and carbon 14, what you have is that you have this excess amount of neutrons. If you see carbon 14 has 8 neutrons, 8 plus 6 is 14, so its atomic weight is 14. We call it carbon 14. This is very unstable. It will continue to lose neutrons until it becomes carbon 13, and then keep losing them until it stabilizes fully at carbon 12. And as it does this, as it puts off energy, it's losing some of that. It still has some. It takes time for that to happen. And scientists have actually dictated that, have actually kind of been able to figure out, calculate how long does it actually take for this atom to go from 14 to 13 to 12. And that's what carbon dating is. So watch that soft talk on carbon dating. It's pretty interesting, I think. Okay, so isotopes, again, unstable until they decay. We call this what we call it radioactive decay to a more stable form of their element. Yeah. Uranium is another really common one that you hear a lot. It's one of the things about why people are so hesitant and against nuclear energy. One of the reasons is because it's very difficult to get rid of nuclear waste because it lasts for millions and millions of years. There's no way to just kind of wait it out. But there's some really good benefits to nuclear energy too. So it's an interesting kind of back and forth. Okay, so now let's talk about chemical bonds because again, life wants to be stable. It wants to be in a steady, lower energy place. And so chemical bonds allow it to do that. They allow it to move to that lower energy place. It's really important to remember that electrons determine bonding. The electrons that an atom has available are what it's going to be able to create other bonds with other atoms with. Because the protons and neutrons are isolated in the nucleus, it's the electrons out there in this cloud that are able to reach out and kind of bond with each other. How much an atom is going to want to bond with another atom depends on its what we call its electronegativity. Electronegativity is essentially how much something wants an electron, right? Electrons are negative, and so maybe electronegativity you would think that's like an opposite thing, but it's not. It's how much does it want that electron. So when we kind of look at these atoms here, we kind of have these atoms with these empty valence shells. So the valence shell is the outer shell. You can see they have these little empty spots where electrons could be filled in because electrons like to be in pairs. They're happiest when they're paired up. And when you only have one, it's kind of lonely. Chameleons are like that. Chameleons don't do well on their own. If you're going to get a chameleon, you need to always have two. Same thing with guinea pigs. I think it's in the UK. It's against the law to only have one guinea pig. You have to have paired guinea pigs. So electrons have to be paired. They want to be paired. They really want to be paired. And when they're not, they're going to be more likely to form bonds. Okay? And so atoms without any vacancies, those are stable atoms. We have examples of those stable atoms. Maybe you can kind of think of some, if you remember your kind of high school chemistry, some stable atoms, things like your noble gases, xenon, argon, those kind of things that just neon, that just exist as they are. Those are completely stable in their outer shells. They don't need to form bonds with other things. They can just be, right? But most other things are going to be unstable without some kind of bond. They need to bond with something else, either themselves or something, some other completely different element to create that full outer valence shell. So here in this picture, you have methane being formed. We take one carbon atom, four hydrogen atoms. This creates this molecule of CH4, this methane. And now you see that each one of these has full valence shells, and so they're all nice, happy, and stable. And methane is very stable. Methane's a very stable gas. It can exist easily at room temperature, room conditions. But not everything is going to form such EC bonds, right? These all kind of have equal affinity for it, right? They kind of have this equal affinity for their electrons, and you see they kind of form this nice even shape where they're all sharing and they're all kind of a nice crisscross pattern, very stable, very what we call a non-polar molecule. Right, there's no unequal distribution in charges. They're all kind of equally distributed around there. Not everything exists like this, though, right? Carbon and hydrogen have similar affinities for electron. They're kind of on the same page, right? They're just on the same wavelength about how intense this relationship is going to be. They have had their talk, they have their boundaries, they've been communicating, they're on the same page. Sometimes it doesn't happen that way. When there are large electronegativity differences, maybe one person is way more invested in the relationship than another person is, then you start to have ionic bonds forming. And with ionic bonds, you're not sharing electrons. One is taking and the other one is giving them away. Okay, so in sodium chloride, NaCl, table salt, very common example. Sodium chloride is an ionic bond in which sodium really doesn't care about its outer electron. It's like, oh yeah, I'd like to have that, but if you want it, you take it, right? Chloride really wants that electron. It's very electronegative. It's so close to having its outer shell filled. It just wants that last little electron. Sodium is actually, hey, if I get rid of this one, I'm going to be more stable. So it's one of those kind of trade-offs where when sodium and chloride come together, they'll form this bond, right? It's really interesting. It actually forms a kind of crystalline stabilized structure when they transfer their electrons. So they kind of transfer and they kind of get into this stable place, this stable bond place. And chloride actually becomes a little more negative because it's gaining an electron, it becomes negative. Put that in your brain, write it down, do what you need to remember it. When something gains an electron, it gets more negative. Electrons have a negative charge, so when you are adding electrons, you're getting more negative. On the inverse, sodium then is relatively more positive. It lost one of its negative electrons. So even though it still may have a fully negative, if we were to test the electricity of sodium or whatever, I don't know if you can do that. But if we were to test the electricity of sodium, it could still be negative, right? But it's a little less negative now. So relative compared to that chloride that just gained more negativity, sodium is now slightly positive. And so it creates these ions. Maybe you've heard that word before. Ions come from ionic bonds. You have a positive ion, a cation ion, and a negative ion, an anion. Right? So ionic bonds form these kind of ionic pairs, where one is going to take the electron, the anion, and the other one is going to give away its electron, the cation. I always remember I like cats. Cats are positive, so cations are positive. Anions, an is a negative prefix that we put on words, and so anion is a negative ion. That's all I remember. Okay, so now let's kind of actually jump back to methane, kind of here at this other end, where you have small electronegativity differences. So if you only have a small electronegativity difference, like I was saying, carbon, hydrogen, they're on the same wavelength, they're on the same page. Oh yeah, we're here sharing our electrons. We call these covalent bonds. When atoms are sharing their electrons, then that's a covalent bond, okay? It happens between atoms with similar electronegativities, so they're kind of on that same wavelength with that, the energy length of that. And it allows to make sure that you're not actually producing ions. There's no ion production. There's no transfer electrons. Hydrogen keeps its, carbon keeps theirs, right? So it's still kind of that in that sense. But it is a continuum, it's a spectrum. And so all the way here at the end, when you have small electronegativity differences, you see we call it a nonpolar covalent. And I mentioned that on the last slide, how methane does not have poles. It doesn't have unequal distribution with the ions. The hydrogens and the carbons make a very nice kind of even intersection with each other. compared to a polar covalent like water, where you have an oxygen in the middle, and then you kind of see the hydrogens are kind of branching off. They're not in like perfect, parallel. It's not like you have a hydrogen at the top and a hydrogen at the bottom or off to the sides. They're kind of at this weird angle. And the reason for that is because in the middle here, in between large and small differences, you have kind of that middle road difference. And that's where water exists. Oxygen is more electronegative than hydrogen, but not so electronegative that it's going to completely take the electron away. It's still going to share the electrons with hydrogen, but it's definitely taking a little bit more than hydrogen is. So again, I like the relationship comparison with this because I think it works pretty well. These kind of relationships where you have one person that definitely takes more, the other people are giving, but then every now and then the one that takes a lot does something really nice. And it's like, okay, well, they do care in their own way, right? So that's kind of how water exists. It's in this polar covalent. And polar here means poles, literally like North Pole, South Pole, positive and negative pole. That's what we're talking about. When you look at a battery and you have it has a positive and a negative end, that's a positive pole and a negative pole. There's an unequal distribution of electrons, and because of that, they're going to want to flow towards each other, and that's what gives you that electrical current that flows when you connect something with a battery. So polar covalent, you have oxygen being a little more negative, hydrogen being a little more positive, and because of that, they kind of bends itself a little. And when we get into the properties of water, we'll talk about this more. But a lot of it really comes down to things that interact with water, that dissolve in water, are polar as well. If something does not dissolve in water, it is non-polar. So methane gas does not dissolve in water. Nitrogen gas does not really dissolve in water very easily, right? They have this that solubility coefficient is what it's called. Oxygen on its own, it can dissolve pretty easily into water. That's why oxygen is so nice for us to be able to breathe. It's a good thing we breathe that. So you have these range of different types of bonds. And it all comes back down to stability. Okay, what does an atom need to do to become stable? Well, if it's surrounded by things that it has a large electronegativity difference with, it's probably going to donate its electrons or take an electron. If it's around stuff where it's like, hey, we're kind of vibing, you're pretty similar, we're pretty similar. Okay, yeah, sure, we can bond, and it works, right? It works. It's a little polar, it's a little bent, but it works. Or you're, surrounded by things where it's like, yes, we very much are on the same page. Cool, we're sharing these electrons. We're really stable. We're really good. Here we go. And then you have your non-polar covalent. I said really good. There's no qualifications on ionic, polar, and non-polar covalent bonds. There's no qualifications in terms of which one is good or bad. Okay. So like I said, water is formed by this covalent bond, and this is a big thing. Properties of water is a huge topic for biology. You need to do it here. We'll talk about biochemistry, a lot of it. So again, water forms by sharing these electrons by these single covalent bonds. One oxygen, two hydrogen forms an H2O molecule, and it gives you these partial negative, partial positive charges. I wonder if I can draw real quick. Okay. So I don't know what, I'm going to skip all of the instructions things, and I just want a blank. Let's see. Well, let me draw. Great. Let's see if this is going to work. I haven't used the whiteboard very much, so bear with me. I'm wondering if it will just let me draw freehand. Yes. Okay, cool. So with water, you have, oh, y'all, my drawing is really bad. I am so sorry. You have an oxygen there. That is supposed to be an oxygen. You have your hydrogens. I have like a trackpad, and it actually makes it harder to draw. Okay, cool. So again, because you have oxygen over here and it's a little more negative, the symbol that we use for that is this weird kind of S where you you connect the tail, and then you put a negative. And that stands for partial negative. And then over here, the hydrogens, we do, again, our little S, connect the tail, and it's a positive. So again, this is the poles of a polar covalent bond. That one kind of looks like a coat hanger. There you go. All right. So partial negative, partial positives by the hydrogen, and that is our polar covalent bond. Okay. I'll take everything out. Yep. Cool. That's fine. I'm going to pull the notes back up. So that shape of water, that polar covalent bond really does make a difference in how water is going to act and interact with other things and with other atoms. Oh, of course, there it was. I should have just looked at the next slide. That's all. That's all on me. So again, this is kind of reiterating what I just said. Since electrons spend more time near oxygen, oxygen has slightly more negative. Hydrogens are slightly more positive. But what's interesting with these types of bonds, because water molecule doesn't always, it never exists by itself. A water molecule exists in a bottle of water, a whole glass of water. So they're always around each other. And because covalent bonds aren't taking electrons, they're sharing electrons, this actually allows molecules of water to form what's called a hydrogen bond with each other. So with hydrogen bonds, one of the reasons why water is the universal solvent, water is required for life here on Earth. We cannot exist without water. It's because of this little thing right here, this hydrogen bond. And a hydrogen bond is going to exist between the oxygen of one water molecule and a hydrogen of another water molecule. Right? So you can see in this picture, you have all these, a glass of water is going to have trillions and billions of billions and trillions of molecules of water. And each of those water molecules, the oxygen is going to be bound to two electrons, right? It's going to be bound to its two hydrogens, but it's also going to have two bonds to other hydrogens from other water molecules. And that's kind of what's going to be for every molecule of water, every oxygen, every hydrogen is going to be bound to another oxygen and hydrogen. It's going to be bound to multiple ones of those. What these help it do is each one is weak by itself, right? This bond right here that's just holding a hydrogen to an electron, that one on its own is very weak, but collectively they're very, very strong. And that's the phrasing you'll always hear, is that hydrogen bonds are individually weak, collectively strong. Those are what give water its properties. And so we're going to go through some of these properties of water here in just the next few slides. This one is just summarizing chemical bonding. Make sure you go through this, make sure you're comfortable with the different types, what the actual basis for that bond is, the chemical basis for it, and then how it reacts, right? The strength and examples. This is a great little summary table for you to be able to quiz yourself or have somebody quiz you on it, ask you questions from it. All right, let's jump into water. So I'm going to go through some of these properties of water a little bit fast because some of them are pretty straightforward and interesting with the Soft Chalks has supplements for it. Okay, so one of the first properties is that water is cohesive. It can cohere to itself, right? So cohesion, when things are cohesive, they're running smoothly, they're nice, they're vibing. And so water will stick to itself really well. This is what gives water its surface tension, its property of surface tension. Why you can see insects walk on things, why when someone belly flops onto water and it kind of flattens out. It's because when you are very quickly with large surface area trying to smack through water, it'll resist you a lot. Bullets do not travel very far through water. That's one of the things that movies actually do get accurate, is that bullets can't travel once they hit water. Their velocity really, really slows down to the point that I'm not sure what the exact depth is, but you don't. It's a diveable depth on a breath to avoid it, because bullets just can't travel through this cohesion of water. It's going to start to stop them. And you can see how it's organized, how it's arranged, that you have these oxygen molecules kind of on top, anchoring themselves down to the hydrogen molecules underneath them. Similar to cohesion is adhesion. Think about adhesive tape. When you put adhesive tape on something, you're probably sticking it to something else, right? You're taping something to the wall, taping something to the fridge, you're adhering it, you're sticking it with tape. So adhesion is allowing something to stick to something else. Cohesion, it sticks to itself. Adhesion, it sticks to something else. I always give the example of watching drops of water run down a window, especially if you're in the car and you're riding in the car, and you kind of notice, well, we're going like 60 miles an hour. Why doesn't this water blow off? Well, adhesion. Hydrogen bonds will form to the glass and allow it to stick there even at high speeds. What is an exception? What can you do to your car to make sure that it doesn't get water stuck to it? Mississippi, 2 Mississippi, 3 Mississippi. All right, wax. Yes, good. You can provide a wax coating on your car. Wax is a fat. Fat and oil do not, fat and water do not mix, right? Oil and water, oil is a fat. Those don't mix with each other. And so by adding that waxy layer, water will just kind of beat up to itself. It'll adhere or cohere to itself, and then it will roll off of your car. Okay. We're showing here in this water molecules being pulled up through the roots of a tree, both properties, adhesion and cohesion. The adhering part is that, yes, it's sticking to the roots, it's sticking to the stems, it's sticking to the leaves, and evaporating out through those pores. So that is adhesion, as it's being stuck to those things, stuck to these vessels. And with cohesion, right? As water molecules evaporate up through the top, because the water molecule that just evaporated was actually attached to the water molecule that's still in the leaf pore, as that one water molecule evaporates, it's going to pull the other water molecule up to the leaf surface with it, and then that one will evaporate, and it will just kind of keep like a little chain of beads, just kind of keep pulling water molecules up along it. And so that's cohesion. So water sticking to itself as it evaporates, kind of pulling the chain up. But then as it goes up the vessels of the tree, water molecules kind of adhere to the sides of the tree. All right, next one. Water is an excellent solvent. Water is the universal solvent. It is the medium in which reactions take place. It dissolves hydrophilic substances. So philic, this suffix of philic means to love is usually the word for it, philia. So to love, to dissolve it, really. Water will dissolve hydrophilic substances. We also call this polar. So things that are polar are also hydrophilic, right? They don't mean the same thing. These are two different words. Remember what polar means if you don't go back a couple of slides. But polar substances will dissolve in water. Same thing with ions. So from your ionic bonds, those are going to dissolve in water. You can see this is probably sugar or salt. This is going to be dissolving very easily, very readily in water. No problems there. With this becomes very important when we start thinking about how we transport things through our bloodstream. Our blood is mostly water. We are mostly water. And so we have to start, our body has to kind of adapt for that. Well, what are the things that are water soluble? They'll be able to transport through the blood, but do you think they'll last as long? Something is water soluble and you're trying to get it from, let's say you're releasing a hormone from your thyroid, from your thyroid down into your kidneys, right? You're trying to regulate. I said thyroid, what am I doing? Your throat. You down to your kidneys, right? That's a long way to travel. What if it doesn't, dissolve by then? So our body has to be able to adapt for fat soluble hydrophobic materials and transporting those. What's actually interesting is that hydrophobic things tend to last longer in the body because they are protected in that way. So again, water is only going to dissolve selected molecules. Hydrophobic things, water-fearing solutes will not dissolve in water. Lipids like butter. If you're ever getting a massage, right? I've been a massage therapist for over 10 years. So people always ask, like, if you get like a really heavy oil massage or you get a lot of oil in your hair, don't try to wet yourself first. What you have to do is get into the shower, soap yourself up completely. Put a layer of soap between you or between the oil and the water. Get soap all in your hair, shampoo all in your hair, and then rinse it out. Because what the soap is going to do, soaps and detergents create these little bubbles, what we call myceles. They create myceles around fat globules. And then, so what happens is the water isn't, the detergent doesn't somehow make the hydrophobic fat water soluble. The detergent is going to surround the fat globule, and then water can wash the detergent away. It kind of holds the detergent bowl, mycel will hold the fat globule. Same thing with grease, same thing when you're washing your dishes. It kind of holds onto and gloms around those fat molecules, and then you rinse that whole thing out. Okay? Those are non-polar covalent bonds, right? Water, okay, keep going through these properties. Water, regulates temperature. Actually, I'm going to jump back just a moment to talk about in the soft chalk, there's a little bit about terminology, solute versus solvent versus solution. So just make sure you're clear about that, right? The solvent is the thing that dissolves. The solute is what goes in it. And the solution is the combination of the two. I always like to use the example of sweet tea. When I go to make sweet tea, my solvent is water. I start with a bowl of water. I add sugar and tea. Those are my solutes. They're going to dissolve and mix in there. And then the actual tea is the solution. Okay, water regulates temperature. If you notice that our body temperatures stay very, very tightly regulated, especially as we get older. If your temperature goes up 1 or 2 degrees, you notice it. When we're kids, it's not as big of a deal. But when we're young, when we're older, slight changes in our temperature are going to really impact us in just much more intense ways. So hydrogen bonds are what allow for water to resist temperature changes. Again, one on its own is not very strong, but collectively, right, you break this one and another one is going to form immediately. And so it takes a lot of energy. You have to put a lot of energy to get water to boil, to get water to change even a little bit of temperature. And so this comes from hydrogen bonds. It cools up slowly. It cools down and heats up very slowly. Think about coastal regions, right? That's a great example. If we here on the eastern part of the state, the coast, and then if you go further east, temperatures tend to be much more mild. They tend to not shift as much because you have large areas of water that are absorbing all of that sun heat and minimizing those temperature changes. Same thing with sweating to cool the body down, right? As we go and release water, as that water evaporates, the heat is taken with it. Water can expand when it freezes. This is a really important property of water because of these hydrogen bonds. It forms these kind of hexagonal structures that actually make it lighter so that frozen water will float on top. This allows for life to continue underneath. When water freezes over in the winter, you have this thick ice layer. That's going to be your coldest part of your water. Underneath, it's actually not quite as cold, and it's going to have space for life to be able to continue existing. Right? It also allows for water levels to be raised and lowered as the Earth climate changes. Okay, so with water being so easily to participate in all of our reactions, we need to kind of talk about some of those reactions. They come down to two main categories: dehydration synthesis and hydrolysis reactions. So all of our biological molecules, all four types that we're going to be learning about later, they're all built through these two main processes, built or broken down through these two types of reactions. Either a dehydration synthesis, and again, let words tell you what they mean. This is my first and most important lesson in biology and in any science class, is the words mean something. Unless it was named after some person, which we're getting a lot better about trying to phase out people's names and replace them with the actual process. That's not that really is just, it just makes it more sense. It just makes it so much more sense. Calling something the Krebs cycle, all right, well, who was Krebs? What does that tell you about something? But the citric acid cycle, oh yeah, that reminds me of the participants involved in this. So dehydration synthesis, you are dehydrating, removing water to create something, synthesis, to make something. So you can see in this reaction, you have two small molecules, okay? And within them, or in between them rather. So I know it's kind of confusing how they've drawn this because they kind of have circled this OH and H, but these are two different molecules. Okay, so you have one molecule over here with two carbon rings, one over here with one carbon ring. And then in the middle, this one over here has a hydroxide, OH, that's hydroxide. This one has this hydrogen. And with a little bit of energy, just a little bit of heat, right, you can actually dehydrate that. You can remove a water molecule and then fuse these three things together. Then if we want to, we could break something apart, right? In that large molecule, let's say that this is sugar. Let's say we're making, these are molecules of sucrose and we're adding another fructose on there, right? And so we want to make this larger molecule. Well, we can do that. We can dehydrate this and create a larger sucrose molecule. Well, now with this one, let's say that we want to put it in, where we want to sweeten up our drink. Well, we're going to take our sucrose, we're going to add it to some water. We're going to stir it around. There's your energy, right? We're going to stir it around a little bit. And then we break it apart. We actually end up with our smaller molecules back out. So again, this is showing dehydration synthesis, dehydrating to make something. I think sometimes people think dehydrate, they think what happens to us and they're like, oh, we're breaking down, like we're kind of falling apart, we're breaking down. So dehydration is breaking down. It's not. You have to remember its full name, dehydration synthesis. Adding water to break things apart, that's called hydrolysis, however you want to say it. Hydro water, lysis means to split apart. To lyse something, is to split it apart. So hydrolysis, you are splitting with water. There are other reactions where we split without water, so just understand this one is fully hydrolysis. All right, I've got a little bit left. Yeah, I can get through pH and then I'll do another video for macromolecules. Okay, so this last one is just about pH a little bit. So pH is measuring the amount of hydrogens in a solution. Okay, and I'm going to get into that. But what you have to remember, and what you probably have known about pH, is that it's talking about acids and bases. Well, water exists as H2O. That's how we kind of know it as, right, as this neutral H2O. But this isn't accurate, right? Water exists in a continuum between H3O and OH plus a hydrogen. And this is what water actually looks like. When you're talking about a bottle of water, there are going to be some molecules that are going to exist as H2O for moments. But a lot of times they're going to be vacillating, switching back and forth between H3O, H2O, and OH. And this is because of hydrogen bonds. This is because of that unequal sharing of hydrogen ions. Sometimes one oxygen is going to be bound to 3 hydrogens, and then sometimes one oxygen only has its 1 hydrogen because its other is all kind of bound to another one. And depending on the amount of hydrogen you add or take away, you can increase that. Right? If we just have neutral pH 7 water, which is the water that we drink, right? Don't drink alkaline water. There's no reason for it. Neutral pH water of 7, a neutral pH of 7. If you add hydrogens to that, it's going to then have more opportunities for hydrogen bonds with oxygen without having to take away from others. So it gives you more chances to form this H3O hydronium than it would be to form this OH hydroxide. Right? So it still happens in neutral water, but again, with neutral water, to form hydronium, you have to take from hydroxide, and eventually hydroxide is going to ask for that hydrogen back. So you're going to kind of always be coming back to this H2O. But if I just take and add a bunch of acid or add a bunch of hydrogens to a solution, well, now I can make H3O without creating OH. Or the opposite, I could take hydrogen out. I could add in things that are going to take the hydrogen, that are going to absorb hydrogens and not release them. So that way I force it to be OH, right? I can remove hydrogen so it can't even form H2O. It's actually just OH. Still exists as water because hydrogen bonds, but most of it will be existing in this OH state more often than in H2O or H3O. So acids and bases, again, pH is measuring the concentration of hydrogens in a solution. How many hydrogens are available in this solution? What is that concentration amount? So acids reduce the pH by adding hydrogens. Bases increase the pH through a couple of different ways. But that's something you go ahead and click in your brain. Acids donate hydrogens. Acids are going to release hydrogen into a solution. That hydrogen is going to bind with H2O to make H3O, which acts as an acid. A base is going to do the opposite. A base is going to actually start to increase the pH of a solution because it can release hydroxide. You can actually add OH, and that OH that you're adding will absorb those extra hydrogens to make more just neutral H2O. They can absorb free hydrogen. So maybe you're not adding OH, maybe you're adding some other type of molecule that can itself just absorb a hydrogen. Our bodies use bicarbonate to absorb free hydrogens, but it's not adding OH. It's not adding hydroxide. You could add sodium hydroxide to something and it would form that water. Bicarbonate, it allows it to absorb that hydrogen. So looking at these 3, you should be able to predict what kind of the structure of these bases. I can go ahead and tell you these are all bases. They're not going to be donating hydrogens. All of these will be accepting hydrogens. But you should be able to predict: is it going to be is it going to be a change in the pH because it's going to release its OH and make water, or is it going to stay as it is and just absorb an extra hydrogen? And I'm going to tell you the answer. You should be able to figure these out. And if you can't, or if you do want to know, email me, and I will tell you the answer then. I'll give you the correct. So here's a pH scale. This is just one version of it. You're going to see tons of different things if you go and look at online for yourself. But the pH scale is organized so that pH 7 is neutral. Anything lower than 7, which here we're going up to go lower than 7. That's why I don't love this image, because I just don't like 0 should be down here to me, not 14, but it's what it is. pH of 0 is all the way up here at the top. That's a strong acid. Okay, you can notice pH of 1, 2, 3. We're talking about lemon juice, soda, tomatoes. Battery acid is down in here with stomach juice. Stomach juice is 1.6 to 1.8 in terms of its pH. So again, if the acidic solutions, if they have a low pH, they have a high hydrogen concentration. So acids have a lot more hydrogens available. Here in the middle, 7 is pure water. Notice milk and saliva are around there. Blood is a little basic, 7.35 to 7.45. Go ahead and learn the pH of blood. And then as we keep going, you see laundry detergent, ammonia, bleach, 11.5, 12.5, and then 14, sodium hydroxide, kind of our strongest base that we'll use ever in most biology labs. Basic solutions have a high pH, closer to 14 or above 7 at least, above 7, and more hydroxide than hydrogen, right? More hydroxide, they're forming water, neutralize or forming that OH base and depriving the extra hydrogens that are available there. So it's making it more basic, or these are more basic solutions. I always like to point out that a lot of times people think acids are more dangerous to bodies, and acids are absolutely dangerous to you. You absolutely can burn yourself. But if you look, lemons, cola, tomato versus ammonia and bleach, which one would you be more likely to eat? I hope there's a very easy answer, right? It should be the lemon juice and the soda. But I always just like to point that out because a lot of times people think that acids are going to be more dangerous, but 100% you have bases in your home that are going to harm you more than the acids would. The acids that you have in your house are probably very much these food-based acids, and they're not really going to be harmful to you. Versus if you mix ammonia and bleach, get out of there, ventilate that space, you just make chlorine gas. And or even just swallowing bleach, right? Even just bleach on your skin, a small burn on the outside of the skin, you'll get those little pink marks and it can really be irritating, annoying. Those are chemical burns from bases. And so I always just like to kind of point that out to folks. Our pH is at 7. That's where most organisms are going to maintain their pH, is at a neutral pH of 7. If we stray, we die, right? Your pH for blood is 7.35 to 7.45. If you get to 6.8 or 7.9, right, about a 0.5 difference, your proteins denature, you die. To help with that, we have buffer solutions in our bodies. And a buffer, think about like when you're playing, if you go play bowling, and they have those little kind of things that they can put up on the side of the gutters to make sure that your bowling ball doesn't go in the gutter. It kind of, your ball might kind of bounce back and forth, right? But it kind of goes straight down the line. That's what buffer solutions are doing. That's what buffers are doing, is that they are buffering. They're kind of keeping your pH right in line. Buffers are able to absorb hydrogens, or absorb hydrogen or release OH or release hydrogen, right? They can absorb and release hydrogens. They can act as an acid. They can act as a base. They can do all of the things. So when pH is too high, right, if our pH starts to get a little bit more basic than it should, buffers will release hydrogens to bring it back. When pH gets too low, it starts to get below that 7.35 to 7.3 to 7.25. That's all it takes, by the way, is your body just has to shift from 7.35. If it drops to 7.32, you're going to start reacting. It's going to start buffering it back. So when pH starts to get too low, our buffer can absorb hydrogens. And here you can see that happening. This is bicarbonate, right? So bicarbonate has 2 hydrogens that it can release. And I'm sorry, this is carbonic acid, and it can release to bicarbonate. That was my fault. HCO3, bicarbonate here, it's able to absorb as more hydrogens get released, as the solution turns acidic, more hydrogens are released. Bicarbonate, if it needs to, it can absorb this hydrogen and become carbonic acid. And it can just stay there as carbonic acid. And then if the pH starts to get too high, it can release this hydrogen, act as an acid, and bring the pH back down. So that's a buffer. This is just one of the buffer systems. You have buffer systems in your bloodstream. You have them in your cells. Your lungs act as buffers. Your kidneys act as buffers. This is why I always rail against a pH balanced water, because I don't know what it's doing. Right? I'm not sure what it's supposed to be doing, because if you are drinking alkaline water, yeah, your blood pH is 7.35 to 7.45, sure, but when you drink it, it's got to go through your stomach, and your stomach pH is 1.6 to 1.8. So if you're drinking, anytime you drink anything, it's going to be higher than your stomach pH, and it's automatically going to get buffered down. And our body's just going to keep doing that. And it's not like we hold on to buffers. It's not like we store them, or you store that extra alkaline stuff. If you don't use it, it just gets excreted. Your body is just going to kind of organize it and incorporate it as it needs to, but it's not going to really do anything. And I always say, if your pH is off, you need to go to the doctor. If your body is not able to maintain its pH, over-the-counter water is not going to help you. You got an issue with your kidneys, you got an issue with your lungs, you got some kind of chemical imbalance in your body. And so there are much bigger problems. And you will absolutely know it. It's not going to be an unknown thing if your pH is not balanced. You will not be well. So sorry, that's my off my soapbox of pH balanced water. So you should be familiar with the scale. You should, kind of definitely spend some time looking at it and kind of talking about it, some the concepts that come with the scale, just because there's some inverse things that happen. Again, that idea that as you go up in pH, as you get more basic, you have less hydrogen. That's a confusing one for folks, right? As you get more acidic, lower pH, more hydrogen. It's also a logarithmic scale. So it's not like if you go from pH of 4 to pH of 5, you gained 1 hydrogen. You gained 10-fold hydrogen. So it's to the 10th. So what that means is that these questions, right? So a pH of 4 has 10 times more hydrogens than a pH of 5. You can calculate that change very simply. You just do the pH that subtract the new pH from the old pH and raise that number, raise 10 to that number, right? So new minus old, raise 10 to that. So 5 minus 4 is 1. 10 to the first is 10. So there are 10 more hydrogens in a pH of 4 than a pH of 5. Okay, what about this one? pH of 10 has 1,000 fewer hydrogens than a pH of 7. Okay, 10 minus 7 is 3. 10 to the third is 1,000. What you have to think about is that we're talking about 10 compared to 7. As we go down in pH, we go up in hydrogens. Okay, so a pH of 10 has 1,000 fewer than a pH of 7. We got the 1,000 because we said 10 minus 7 is 3, 10 to the third is 1,000. So that's how we got that part. Then we had to remember, okay, yeah, we're going from 10 to 7. If I'm going down in pH, I'm going up in number of hydrogens. So 10 has to have fewer than 7. Okay? This first one, 4 has 10 times more hydrogens than 5. All right, well, 4 is lower than 5. So yeah, if I'm talking about 4, then 4 has more than 5 would. Right? If I said 5, I said, oh, a pH of 5 has 10 times less hydrogens than 4. You see how it can kind of work that way. It just is a little confusing if you're not used to it. So take some time to kind of flip back through that. Okay, I think that was it for the this part of the lecture. It went a little bit longer than I normally was planning to, but hopefully this was helpful, and I will record a 2.5 sometime later this week. Thank you.